In VAR, SVAR and VECM models, the impulse response functions estimate the impact or effect of an external shock to the variables in the system over time. Impulse response functions involve an external shock to the variables, known as impulse. The effect of that impulse on the system of variables can be traced over time, known as the response. IRFs are one of the most important applications of the VAR, SVAR and VECM models. They are used to study how the exogenous structural shocks can affect the variables over time. An important thing to note here is that IRFs are generally estimated using structural shocks or errors, and not VAR residuals. That is, the IRFs mostly used in practice are based on structural VARs instead of reduced-form VARs. The structural VAR models incorporate contemporaneous effects, and certain variables can affect other variables in the same time period. In reduced-form VARs, on the other hand, there are no contemporaneous effects. Here, we will discuss the relationship between reduced-form VARs and structural VARs or SVARs. We will focus on deriving the impulse responses using structural shocks and VAR residuals and how to incorporate contemporaneous effects using orthogonalized impulse responses. To understand the relationship between reduced-form VAR, structural VAR and their innovations or shocks, let us consider a basic reduced-form VAR-1 model with two endogenous variables x and z. Such a model can be expressed as shown in equation 1, where A1 is a coefficient matrix associated with the first lag of variables and mu-t is a vector of reduced-form innovations or residuals. In equations 2 and 3, we have expressed this model in the matrix form and the equations form, respectively. As we can see, this reduced-form VAR does not contain any contemporaneous effects, that is, the variables x and z do not affect each other in the same period or instantly. Hence, variables x and z affect each other after a time lag. However, a structural VAR or SVAR model allows us to include contemporaneous effects. Let us take a look at how we can express an SVAR model with variables x and z with one lag and contemporaneous effects. Equation 4 shows a typical specification of the SVAR model, which includes contemporaneous effects. The variable z affects x in the same time period and x affects z in the same time period as well. Equations 5 and 6 express this SVAR model in the matrix form, and this is how structural VAR models are typically specified. The matrix A is a k by k matrix, which contains the contemporaneous effects of variables x and z on each other. The matrix theta1 is also a k by k matrix containing the coefficients of the first lag of the variables. The vector epsilon contains epsilon xt and epsilon zt, which are the structural form errors of the two equations of the model. Moreover, these structural form errors are white noise and uncorrelated. In some SVAR specifications, you will see these structural form errors epsilon being correlated to structural shocks E as shown in equation 7. The matrix B here is also a k by k matrix. As a result, we can substitute this equation 7 in equation 6 and also specify the SVAR model as shown in equation 8. The SVAR model cannot be estimated using OLS because of the simultaneous equation bias. Hence, we need to introduce some restrictions to make the SVAR model identified. This specification in equation 8 is used when estimating SVAR models because we can choose to introduce restrictions in matrix A and in matrix B. However, we are not interested in estimating SVAR model in our example, we are only interested in impulse responses. So, we will continue with the SVAR specification used in equation 6 earlier. Since the SVAR in equation 6 contains contemporaneous effects, it causes simultaneous equation bias and cannot be estimated using OLS. We convert this SVAR model into a reduced form VAR by pre-multiplying equation 6 by A inverse. This reduced form VAR can now be estimated using OLS. Moreover, the reduced form coefficients and innovations are related to structural VAR coefficients and errors as shown here. The constant of reduced form VAR is equal to A inverse multiplied by theta 0, where theta 0 is the constant of the SVAR model. Similarly, the coefficient matrix A1 is equal to A inverse multiplied by theta 1. More importantly, we can also see that the reduced form innovations and structural form error terms are also related. Reduced form innovations mu-t are equal to A inverse multiplied by structural form errors epsilon t. Therefore, we can obtain the reduced form innovations from the structural form errors as shown in equation 9. The term highlighted here is simply the inverse of matrix A. Matrix A is the same one that we defined in equation 5 and equation 6 earlier. As a result, we have established the important relationship between the reduced form VAR, structural VAR with contemporaneous effects and their innovations. This relationship is critical, and we will use it later to derive the impulse responses, which will also include contemporaneous effects. Similar to univariate autoregressive models that have a moving average representation, the vector autoregressive or VAR models also have a VMA or vector moving average representation. This vector moving average or VMA representation expresses the variables in the reduced form VAR system as functions of its innovations or residuals. Hence, they are useful in deriving the impulse responses where we wish to study the effects of shocks on the variables. Let us continue with the same VAR1 model we specified in equations 1, 2, and 3 earlier. These equations show the matrix and equation form of the VAR1 model with k equals 2 as we have two endogenous variables x and z in the VAR model. Here, mu-t contains the innovations of this reduced form VAR, and our objective is to express the variables x and z as functions of these innovations. We start by iterating backwards as shown in equation 10. Equation 10 simply expresses the VAR model in terms of the previous lag, where yt-1 is a function of yt-2 and previous period innovations or shocks. Next, we substitute this equation 10 into our original VAR model in equation 1. As a result, we can express the variables in yt as functions of yt-2, innovations mu-t-1 and mu-t as shown in equation 11. We arrived at this equation by iterating backwards for one time period. In a similar way, we can iterate backwards n periods to arrive at the equation 12 shown here. This represents the variables in yt as function of current and previous n period innovations and yt-n-1. At this point, we must make a critical assumption that the VAR model is stable, that is, the variables in the VAR model are stationary. This further implies that as n approaches infinity, the matrix A1 raised to the power n vanishes. This assumption allows us to express equation 12 as a function of innovations and unconditional means of x and z as shown in equations 13 and 14. As we can see, the unconditional means of x and z will be constant and are a combination of different coefficients of the VAR model. Since they are constant, we have expressed the variables x and z as function of only reduced form innovations, and this is known as the vector moving average or VMA representation. This VMA representation in equation 14 will allow us to estimate the impulse responses. It is based on the assumption of stability of the VAR model where the variables will also be stationary. This assumption further means that the effects of shocks will only be temporary in a stationary VAR model. After the shock, the system will converge back and the impulse responses will fall to zero with time. The equation 1 and 2 represent the reduced form VAR model we defined in the beginning. Equations 13 and 14 show the vector moving average or VMA representation of the reduced form VAR model. This VMA representation shows the endogenous variables x and z as functions of the reduced form innovations mu-t-i. However, we want to analyze the effects of structural errors on the variables and not the reduced form innovations. This is because the structural form errors are based on the SVAR model, which allow us to include contemporaneous effects. Therefore, we must define the variables x and z as functions of structural form errors and not just the reduced form innovations. In equation 9 earlier, we derived the relationship between the reduced form innovations mu and the structural form error epsilon as shown here. Hence, we can substitute this equation 9 into the VMA representation in equation 14. This gives us the equation 15 shown here. As we can see, equation 15 expresses the variables x and z as functions of structural form errors epsilon, which is exactly what we need to estimate the impulse response functions or IRFs. We can simplify this by defining the coefficient phi as shown in equation 16. This will give us the simplified equation 17, which is how the impulse response functions are estimated. In this equation 17, the different phi coefficients represent the IRFs, that is, the effects of different shocks on the variables x and z. The coefficient phi11I shows how a shock to epsilon xt will affect the variable x. Similarly, the coefficient phi12I shows how a shock to epsilon zt will affect the variable x. On the other hand, the coefficient phi21I shows how a shock to epsilon xt will affect the variable z. The coefficient phi22I shows how a shock to epsilon zt will affect the variable z. Moreover, the I in these coefficients represents the time period. For instance, phi120 will show the contemporaneous or instantaneous effect of the shock epsilon zt on the variable x. Similarly, the coefficient phi121 will show the effect of shock epsilon zt-1 on the variable x or the effect of shock epsilon zt on the variable xt+1, that is in the next time period. We discussed earlier that the SVAR models cannot be estimated using OLS because they include contemporaneous effects leading to simultaneous equation bias. We need to introduce some restrictions on the variables to make the SVAR model identified. As a result, the impulse response functions are also based on some restrictions on variables when we include contemporaneous effects. In SVAR, there are several different ways to impose restrictions. Since the focus is on impulse responses and not SVAR model itself, the most commonly used restrictions are based on Cholesky decomposition. These are also known as orthogonalized impulse response functions. Under the Cholesky decomposition, the ordering of variables becomes important in the SVAR model and IRFs. For instance, in our VAR model example with variables x and z, we can choose to order the variables in two ways. First, we can order them as x followed by z. In this case, only x is allowed to affect z contemporaneously or in the same time period. The other way is to order z before x, where only z will be allowed to affect x contemporaneously or in the same time period. Hence, the ordering of variables determines which variables can affect others in the same time period or instantly. Let us consider an example where we have three variables: income, consumption, and investment in the VAR model. Suppose we choose to order the variables as income first, consumption second, and finally investment. Under the Cholesky decomposition, it means that only income will affect both consumption and investment contemporaneously because it has been ordered first. Consumption is ordered second, so it is allowed to affect only investment in the same period. Finally, investment is ordered last, so it will not affect income or consumption contemporaneously. Investment will only affect other variables after a time lag. Hence, restrictions are imposed on the variables in such a way that some selected coefficients associated with current period are restricted to 0. The selection of those coefficients is based on the ordering of the variables. In software programs, when we estimate orthogonalized IRFs after VAR model, where we allow some variables or shocks to affect others contemporaneously, this type of ordering and Cholesky decomposition is often applied by default. Thank you for watching, and I will see you in the next tutorial.